All right, this is the second video, finishing up our unit on rotational motion. In the first video, we concentrated on the definition of what angular momentum is. And we saw that we could express it for a point mass that was moving with some momentum, or we could also talk about a rigid body that had a particular rotation. Now what we're going to concentrate on is the idea of the conservation of angular momentum. And this is really going to help us hone in on this fourth LO that you're going to be looking at on next Monday. So what did we find? We found that this rotational equivalent to F equals ma could be written as the sum of torques is equal to the angular momentum, the time rate change of angular momentum. But what if we don't have any external torques? If we do, then we say that the derivative with respect to time of the angular momentum is 0, which we know from math class means that the angular momentum is constant. So remembering that for a rigid body, which is something we'll work with a lot for these types of problems, the angular momentum can be written as the moment of inertia times omega. And so then we can write conservation of angular momentum, which we found would apply if the sum of the torques was equal to 0. We could say that the initial angular momentum is equal to the final angular momentum. If we just have a rigid body that's rotating with some particular angular velocity, this could be rewritten as the moment of inertia times angular velocity for both before and after. And then we can see what would happen. If I decreases, it'll cause the angular rotation rate to increase and vice versa. If our moment of inertia increases, our rotational velocity will decrease. And so there's some interesting applications of this. So this is a classic classroom demonstration where you have someone standing on a turning turntable with weights extended from their body. And so in this case, you would have the moment of inertia of the person and the stool, but then you would also have these two masses. And so these could be treated as mr squared for their contribution to the moment of inertia, and you have two of them. So you have this overall moment of inertia, and if we start this guy rotating at a relatively slow rate, because we don't want him to fall, look, he's old, he has gray hair. If he pulls in the dumbbells, the R initial goes to R final, which is going to decrease, and that means that the moment of inertia at the end is going to be falling, which is going to really increase his angular rotation. You've seen this type of thing happen with like figure skaters. In that case, they don't have to carry around dumbbells, but they just use literally the mass of their arms. And as they pull them in, decreasing their moment of inertia, they increase their angular velocity without anyone out there pushing them to make them go faster. So let's think about sort of this problem initially, or like how we would solve this problem. So let's just say that the moment of inertia of the man and the stool, just in general, we are given a value of 1.5 kilograms meters squared. We're going to say that the initial distance of the dumbbells is 0.75 meters, and the final distance of the dumbbells is 0.1 meter. Each dumbbell is going to have a mass of 2 kilograms. So the initial moment of inertia in this situation is that of the man and the stool, and then plus each mass, so two of them, the mass of the dumbbell times their initial distance from the center of rotation. So we get 1.5 for the moment of inertia of the man and the stool, plus 2 times the mass of each mass, which is 2 kilograms, and then the 0.75 squared. And so the initial moment of inertia of this arrangement is 3.75 kilograms meters squared. In the final situation, we have the man in the stool. That doesn't change ever. But we have our mass of our dumbbells has moved to a different location, so that number will change. And the final moment of inertia is 1.54 kilograms meters squared. Let's say that omega initial is 1 radian per second. We want him to rotate kind of slowly. And so if we do conservation of angular momentum, writing the angular momentum as the product of the moment of inertia and the angular velocity, we can solve for the final angular velocity. And we find that his spin rate increases by almost 2.5 times and all he had to do was pull the weights in. So this is a classic moment of inertia problem. Let's look at some questions. So if I have a thin rod of length L and mass M, so here it is. It's rotating with an axis through its center, so I'm going to put it there. And initially we have a small mass on either side, so these are my little masses, little m's. And they're about halfway from the edge, and everything is rotating with S. And then what happens if we move the masses to the ends? So this is the initial case and this is the final case. So again, we're looking at the conservation of angular momentum. And you have to ask yourself now, if I move these masses outward, what's happening to the moment of inertia? This is actually the man on the stool problem in a sense, but backwards. As they move outward, the final moment of inertia is going to be bigger than what it was initially, because now I have these masses at this larger distance from the axis of rotation. So their contribution to the moment of inertia of the system is going to be bigger than it was initially. And so if that moment of inertia is bigger, that means that omega final is going to go down. So the answer will be that it's going to decrease. Now, what happens if they fly off? So here, the idea is that the masses actually, as it rotates, they're not being held onto the rod. And so if everything is rotating like this, what if one mass goes like this and the other one ends up going like this? And so what we might think about is, before we thought of their contribution to the moment of inertia was equal to 2 times their mass times their radius squared times omega. But now what we could see is their contribution can be written as 2 times their mass times their velocity times their radius, because now we think of them as moving linearly. However, remember that their velocity that they have is going to be determined by how fast they were rotating anyway. And we notice that if we substitute in this for velocity, the radius times the angular velocity, we get this term, then it simplifies to exactly what we had before. And that's what can be kind of tricky. I think our first instinct is that if the beads fly off, we would think that the rod would slow down, because we're almost thinking of them being lost to the system. But we would still think about their contribution to the overall angular momentum, and it turns out that even when I write it in terms of their linear motion, their overall contribution to the angular momentum is exactly the same as it was the moment before they flew off the rod. And so the rotation rate of this system is not going to change. Another interesting question is for the figure skater, again, pointing out that this problem is essentially the same as the man on the stool. What is going to happen to the angular momentum and kinetic energy of him as he pulls his arms in? And we know that if he has some initial moment of inertia and some final moment of inertia, his final moment of inertia is less than it was initially, so he's going to be increasing his spin. And that is actually through the conservation of angular momentum, is how we know that. So we basically know that this cannot be an answer, and this cannot be an answer. So is it B or D? So the question is, what happens to the kinetic energy? Does it change? Let's take a closer look at that. The initial kinetic energy is 1/2 his initial moment of inertia times its initial angular velocity. His final kinetic energy is 1/2 I final times omega final squared. And what we want to do is we want to be able to compare these two quantities. So we want them to be written in terms of things that we know. So what could we do? We can use the fact of conservation of angular momentum to try to sort of rewrite this. So what if I substitute in for omega final, omega initial times the moment of inertia initial times omega initial over moment of inertia final. And so I'm going to take this and I'm going to put it in here. So we got kind of a mess right now, but let's try to simplify it. I'm going to get rid of one of these, and I get 1/2 I initial squared omega initial squared over I final. We might be feeling a little despondent because this looks messy, but what if we try to take out 1/2 I initial omega initial squared, and then we'd have to multiply that by I initial over I final. And this is all to write the final kinetic energy. So K final, now this is actually the initial kinetic energy. So we could say that the final kinetic energy is equal to the initial kinetic energy times the ratio of these moments of inertia. And this is a value that is bigger than 1 because the moment of inertia of the figure skater when he had his hands outstretched is greater than it had when he had his hands in. And so K final is definitely bigger than K initial. So what we can say is, in conclusion, like we can say L stays the same and K increases. But we might ask ourselves, why? Why does the kinetic energy increase? What we've learned so far is this means that there's been work done. How was the work done? He had to exert a force to pull his arms in. Work. So he actually, it's interesting, and sometimes I have a figure skater in the class that can attest to this. but it's actually difficult to pull his arms in. He actually has to pull them in, and as he's doing that, he's doing work, and that is why his kinetic energy is increasing. A lot of times people feel like, well, because angular momentum was conserved, we think kinetic energy will be conserved as well. But it's not exactly true, because they depend on moment of inertia and omega in different ways. Remember, kinetic energy depends on omega as squared, and angular momentum relies on it as just omega. And that's why they don't act exactly the same. But it's an interesting result that we might not have expected. Finally, we're going to do one last problem, and this is where we have a bullet's going to hit the edge of a disc and become embedded in it, and then it's going to start spinning together. So initially, the angular momentum initially is going to totally come from the bullet, and then in the final case, it's going to come from the bullet and the disc, because initially this is not rotating. So the initial angular momentum is going to be given by the mass times the velocity times the radius. And so that's going to be 0.002 times 500, and then the radius of the disk is 0.5 meters. So that initial moment of inertia is, I didn't write it down. It's just 0.5. Now, the final moment of inertia is the moment of inertia of the disk plus the moment of inertia of the bullet. The moment of inertia of the bullet. This, what I really wanted to write was this, sorry. So this is 1/2 the mass of the disk times the radius squared plus the mass of the bullet times its radius squared. So the final moment of inertia of the system is 4.005 times 10 to the minus 3, that's 10 to the minus 4 kilograms meters squared. Okay, so go to the next page. So the initial angular momentum was 0.5. The final moment of inertia was 4.005 times 10 to the minus 4 kilograms meters squared. So initial equals final, 0.5 equals I final, omega final equals 4.005 times 10 to the minus 4, omega final. Omega final turns out to be 1.25 radians per second. So hopefully that makes sense. So this was the moment of inertia due to just the bullet, which was just mv times r, because that's how far away it was from the axis of rotation, axis right here. In the second case, we had the mass of the bullet and the disk had a final overall angular momentum, which we had done in the previous page. And we multiplied this by the final angular velocity, which we could then solve for, and we found that it was 1.25. And so that is what we conclude with. Hopefully you feel confident in doing conservation of angular momentum problems, but of course you should always be doing your homework.